Thank you, Nico. You can see he has a lot of letters after his name. He is a professor at the University of Uppsala in Sweden, one of our leading geologists, and this afternoon is here with us once again on board Seaborne Sojourn. So ladies and gentlemen, please give a nice warm welcome back to the fantastic Professor Valentin Troll.
Thank you very much. Robert, thanks for the kind introduction. And yeah, it's always a pleasure being here. And today I'd like to talk a little bit about volcanoes and the not so good things volcanoes do. I'm also going to give a lecture later in the cruise about the good sides of volcanoes, because like every person, there's good and bad sides to everyone, and that's true for volcanoes as well. But today we're going to do the not so pleasant side, because we're actually approaching the island of Lanzarote. And Lanzarote had a big volcanic eruption between 1730 and 1736. And many of you will have the opportunity to look at the Mountains of Fire, as it's called, the eruption site at Timanfaya. It's a local, aboriginal local name, Timanfaya. And there, 23% of the entire island got covered with lava and ash. It was actually one of the very earliest volcano evacuation efforts led by the King of Spain. And only years after the eruption, the people came back. And when we talk about the good side of volcanoes, I'll bring you some information about that, because the eruption was devastating. But after the eruptions, the local people learned to use volcanic ash in agriculture. And within a few decades, this revolutionized the island. Suddenly, they could grow all sorts of crops. They could grow wine, they could grow fruit, which wasn't possible beforehand, and the population doubled in less than 30 years. So volcanoes are not just bad, but today we're going to look at the not so good sides, as I said. So let's plunge right in. When we see a volcano at the surface, then, well, we are familiar with this cone shape. Lava that erupts, ash that erupts, builds up and forms a cone. But I should stress, the nastiest volcanoes actually don't have cones. The really nasty volcanoes are not easily recognized. And we'll talk about that a little later as well. And like with icebergs, the cones are only the tips. We actually have a vast system of feeders and magma chambers, or reservoirs we call them these days, attached to this, all the way down to a source region in the mantle. So this volcano magma system, as it's commonly known, is bringing magma from deep inside the earth via various storage and holding chambers, via conduits to the surface, and then only a fraction of this magma ever erupts. And estimates go between about maybe 10 to perhaps 20% of magma will actually reach the surface. Most of the magma will get stuck along the way. So another kind of important thing to cover straight away, I feel, is this notion. A lot of people kind of say, Val, is it possible that we have more volcanic eruptions than ever before? I see it in the news all the time. And if you look at this chart from the Smithsonian Institute in the US, then the upper red line, it shows the reported volcanic eruptions. And indeed, it seems to go upwards quite dramatically. So it would imply that we have more volcanic eruptions. But if you look very carefully, there is strange anomalies in that curve. Whenever there was a big volcano eruption, we seem to actually find more volcanoes erupting afterwards. And whenever the world was busy with other things like World War I or World War II, volcanoes seem to not erupt quite as frequently. And of course, this is an artifact. There is no such thing. I mean, when humans are busy, they don't look for volcanoes. And when there was a big eruption, then we'll see suddenly things everywhere. So this is the reality, that we don't actually believe that there is more volcanic eruptions right now than there used to be in Earth history, at least not in recent Earth history. And we can see that when we look at the lower curve here. The lower curve is the intensity of volcanic eruptions recorded, and that's a pretty flat trend. There is not a lot of change. In addition, let me show you this graph here on the left-hand side. There we also see the number of known volcanoes. So actually, it is correlating with the number of reported eruptions. In simple terms, we learn a lot more every year. We see a lot more. We realize there's volcanoes in remote areas that we can now monitor with remote sensing, with surveillance equipment. All of these things weren't possible 100, 200 years ago. And therefore, it looks in reported numbers as if there is more volcanic activity, but in reality, there is very little evidence for that. So let me bring you now to the rest of the talk, and here's a little summary. We're going to cover some background on volcanoes. We're right in the middle of it, in fact. Then we're going to look at direct hazards from volcanoes, but also indirect hazards. And then we're going to close with a little bit of volcano monitoring and hazard mitigation, i.e., what can we do about volcanoes? How can we understand volcanoes? How can we actually forecast the events that are threatening us from volcanoes? So the central effort here is the recognition of direct and indirect effects of volcanic eruptions, and then the mitigation. So this is what my day job is all about. We need to understand volcanic phenomena and ideally make some sensible forecasts about what could happen if this or that comes to play. And here's some beautiful drawings and paintings from Vesuvius in the Bay of Naples, and it looks rather scenic on the left, at least. On the right, it's a little bit more scary. And knowing that this is the volcano that wiped out Pompeii gives it a slightly different dimension. But I'm using this here to illustrate that humans have been interacting with volcanoes for, well, as long as humans are around. And in certain cultures, we have learned to live quite well with volcanoes. In others, we're still struggling. The different volcanic hazards, they are shown in this little diagram here. And there we have distance on the x-axis on the bottom, and then we have time as well in the upper part of the diagram. So we have immediate effects very close to the volcano, like lava flows, like ash that's raining out. But ash can also be transported a bit further away from the volcano with the wind, so it can travel for hundreds of kilometers, for example, and it may be in the air for days to weeks, and potentially even months. And then, of course, we have, in large eruptive situations, we have impact on climate even, and this can affect, well, global climate for years. After the Krakatoa eruption, 1883, we had strange weather phenomena. The year without a summer, 1816, after the Tambora eruption, it changed political history, it changed military history, because suddenly, well, rivers that should be passable were not, and the other way around, and this, of course, makes a huge difference. So volcanoes have huge effects, and some people even speculate that in 535, there was a big eruption at Krakatoa volcano, and it may have even caused the collapse of the Roman Empire. It seems to correlate in time. How true it is, I don't exactly know, but it is possible, because grapes will not ripen, food will go off, it's going to be very wet, and therefore all sorts of political turmoil may ensue from large volcanic eruptions. So let's talk a little bit more about direct volcanic hazards to start with. So the direct ones, they are, of course, in the vicinity around the volcano. Here's some images from Hawaii, from Etna, but also from La Palma, and this is lava flows. Lava flows are probably the best known volcanic hazard we're dealing with, and these direct hazards, well, they can be very destructive to immovable objects and also to people who actually get trapped in those situations. Two eminent French volcanologists, Katja and Maurice Kraft, they distinguished volcanoes into principally two types: the black ones and the red ones. The black ones are pretty harmless, the red ones are not. So we'll start with the black ones now, and black comes really from the black basaltic lava that these volcanoes are producing. Oops. Let's go back here. So, and the black ones are the ones in the top right-hand corner of this little illustration, and the red ones are the ones in the left with the big eruption columns. Why are they red? Well, it's because if you have ash blown into the air, there will be an interaction of the volcanic particle with the air. It's oxidizing, and it's basically a form of rust. So the rock that is hot will actually oxidize, they will rust a little, and therefore they have sometimes a red appearance. So that tells us that there was explosions, that there was interaction with the air because the material was blown up high, and this is what we describe here in the lower left of the diagram, Pelean eruptions and Plinian eruptions, where material is thrown up potentially kilometers into the stratosphere. So black volcanoes are characterized by lava flows, and these are usually basaltic in nature. That means they have low silica content of about 50%, and they can affect areas up to maybe 10 kilometers away from the volcano, give or take a little bit. And they can occur at many volcanoes, but they kill very, very few people. Most people are quite aware of lava flows in their area, if there is some, and they travel. The fastest ones I've seen is about 30 kilometers per hour, so this is maybe the speed of a moped. So you can just about make it, if you're warned ahead of the lava arriving, you should be able to evacuate your property. And then maybe your house gets lost. Immovable objects will, of course, not be saved in those situations, but they don't really kill people anymore. It takes quite a long time for lava flows to become soil, and I should point this out as well. Often lava that erupts will actually devastate an area, like we've seen in La Palma in 2021. The agricultural loss, the economic loss from lost agricultural land can be very severe, and it takes about up to 1,000 years or so until soil is really coming back onto fresh lava. So here's an image. This is from Hawaii, and this is a Hawaiian term that's often used, pahoehoe lava, and that's lava with a very smooth surface. There are several interpretations what the term actually means. Some people say it's a rock that is so smooth you can walk on it with your bare feet. Other people say it's actually a description of the ocean surface on a calm day. In any case, it means very smooth surfaces. And often we also have ropey textures in that case. Here's an example from El Hierro, and there we have these flowing lavas, and they flow quite smoothly at reasonable speed. And well, they can cover roads and they can flow around houses. But as I said, they don't really kill people anymore unless you're a bit, adventurous and get too close. So I have a little video here. This is actually just from earlier this year from Iceland. Let's see if I can get this going. This is a little pahoehoe lava on a very calm day. And you see it's flowing very gently. And I think you get the idea. This is not something that is too dangerous if you are standing a few meters away. And if this happens on a larger scale, like on Hawaii, for example, we often have large flow fields. And here we have a large flow field from Hawaii, and there's a geologist for scale. And there we actually have some flow under the surface. And there we make a little lava tunnel at this particular point. But lava fields are a little dangerous. If they're too fresh, you shouldn't walk on them without knowing the detailed structure of them. Because of these lava tunnels, there is, of course, a chance you could break through. And here we have lava lakes. This is also from Hawaii. This is often depressions where lava flows in, and then the lava takes quite some time to cool. It could take years. And then you have a lava lake, and the lava lake will start to form a crust, but it's often still liquid in the interior. So here is a lava lake from Hawaii, and I guess after a while you can walk on this. It's like a frozen lake, but there's still hot lava inside. Now, I'd like to talk a little bit about A'a lava, and that is blocky lava, and that is fundamentally different to pahoehoe lava. A'a lava travels differently, and it's much more spiny. It's not nice to touch, certainly not nice to walk on with bare feet. And this is actually also moving, as I said, in a very different way. So this is how it moves. It doesn't just flow like a liquid we're familiar with. It's actually more like the chain of a caterpillar. So the approach of the lava is fundamentally different, and this often leads to misconception. In La Palma, people were trying to save a church, and they dug a trench. The idea was that the lava would actually approach the trench and then get channeled away. But our lava travels fundamentally differently. It rolls over things. It doesn't care whether there's a little trench or something like that in the way. And of course, despite all the effort, the church of Todoque in La Palma was not saved. And this is a fundamental problem here, to understand the different types of lava you're dealing with, and that can help you to actually make some central forecasts and predictions. The concept of this is actually well known. It goes back to several hundred years ago. Here's a drawing from Vesuvius, and you can just about see the flow patterns in the upper part of the volcano and the more rubbly part in the lower part. So I think the artist here actually captured this already a few hundred years ago. And here's another one where you kind of get the sense that the rubbly nature is depicted in the lower part of the lava flow. And indeed, what happens is when the runny lava cools, it starts to get more blocky. So our lava is a result of cooling of the Poi lava. And well, these effusive events here, they are, as I said, not a threat to life anymore, but they are a threat to property. And our financial losses are skyrocketing right now, certainly in Europe. We had eruptions at Etna, we had eruptions in La Palma, we have the Iceland situation, and it destroys roads, it destroys water pipes, it destroys electricity grids and houses. So this is financially a real worry for the years to come. So, and let me show you this little video clip, which was from La Palma in 2021. This is an AA lava that is caterpillaring its way over a little house. So, and I should add that while the house was then collapsed, the geologists were all really interested to go closer, but then little did we realize there was a gas tank inside the house. So, and then the house blew up after it collapsed. Anyway, there was not much we could do. This was not to be saved, and here is another example of this. This is the Heime eruption of 1973 in Iceland, and Heime is a very spectacular case of where people claim they stopped an AA lava flow. And the story is that the harbor basin was threatened to be filled up with lava, and the local fire brigade brought in the fireboats, i.e. boats that could spray water on the lava, and the lava stopped moving into the harbor entrance, and apparently the harbor was saved. Well, it's a wonderful story, but volcanologists know that's not how it works. If the lava wanted to travel forward, if there was enough new lava coming out of the volcano, it would not stop. A little bit of spraying water would not have any effect. So these urban myths are partly damaging because they make people believe that you can do something that is actually impossible, like, as I said, with the church in Todoque. So I feel it's important to clear this up. Well, lucky for Heime, the harbor is still active, but it's not because of the fireboats. So another large type of basaltic eruption that is actually unpleasant is fissure eruptions. And what we see right now on the Reykjanes Peninsula in Iceland is small versions of those fissure eruptions. The nastiest we had was the 1783 Laki eruption on Iceland. It actually erupted for several years, and it sent out clouds of fluorine gas. And this was very poisonous. And it's estimated that it led to a large famine by killing a lot of, well, livestock, first of all, and then people as a consequence of that. And it's known that the gas clouds traveled all over Northern Europe. It's reported that there was strange poisonous haze in Ireland, in the UK, and also in Scandinavia, actually. And you can actually see in the church records, for example, in southern Sweden, that there was higher mortality in the years after the Laki eruption. So Icelandic volcanoes do not only cause air travel problems, they can actually really kill people, even quite remotely. So this was the black volcanoes, and I'd like to move now to large shield volcanoes, just as a passing note. And here, shield volcanoes are termed shield volcanoes because they resemble a warrior's shield that's lying flat. And we have Hawaii being a shield volcano, but the biggest shield volcano we actually know of is on Mars. And this is Olympus Mons. Why is the volcano so big? Well, because there is no plate tectonics on Mars. When you have a pipe of lava or magma rising up and plates are moving, then you distribute the lava on the surface. But Mars doesn't have plate tectonics, so it continues to pour out at the same place. And this is why we have this ginormous volcano here on Mars. And not only is it a big shield volcano, it also has a caldera on top, a collapsed structure, the little circular bit on top. And we have calderas on Earth as well. These are actually the not so obvious but very dangerous volcanoes because they often explode explosively. An intermediate type between black volcanoes and explosive red volcanoes is Surtsayan volcanoes. And these are named after the eruption at Surtsey in 1965. They're close to Heimaey, in fact. There was a little eruption that was under the water, and as soon as the volcano under the water reached very close to the ocean surface, you started to get a lot of steam. When water is converted to steam, it increases in volume by factor 1,000. And that will actually cause explosions. Well, dynamite has a factor of 20,000, so it's even more effective than water and lava. But there you have this expansion of the water, and it leads to these hydromagmatic explosions. And we call them now Surtsayan after the descriptions we have from Surtsey in 1965. So here's a few impressions of Surtsayan eruptions, and they can be very unpleasant if you're close by, so it's not recommended, but they are usually dwarfed by volcanoes like this, the red volcanoes. So this is Mount St. Helens in 1980, and this is during the height of the eruption. This is the eruption column being a feeder towards ash plumes in the area, and the ash was rising up several kilometers into the air. So the greatest risk from volcanoes is actually these pyroclastic flows. Pyro is fire and clastic is broken, so broken by the fire. Ash is lava that's broken by the fire. And these are very dangerous volcanoes. They usually occur in a tectonic situation that we call subduction zones. That would be Japan, Indonesia, the Caribbean, Northwest America, and of course also the Andes. And there they contrast these basaltic systems that erupt in a benign way, and these volcanoes, they contrast by producing these large eruption clouds. And the typical one, or the worst one you can imagine, is the Plinian type. And this was described from Vesuvius by Pliny the Elder in 79 AD. And this one would actually reach the stratosphere, so that it can reach a height of 12 kilometers. So why do they actually erupt explosively? Well, the silica content of these magmas is different, it's higher, and that makes the magma under the surface very stiff. It doesn't flow so easily. And when you have gas in there and gas decompresses, it starts to make bubbles, and the bubbles will grow the more the lava rises up. And at some point, the bubble growth will outpace the movement of the lava, and then the lava fragments, it shreds. The phenomenon is very similar to a champagne bottle. When you actually decork it, the bubbles will grow faster than the liquid can respond to it. And this is why you get a jet of champagne coming out. It's a bit more pleasant than at volcanoes. But yeah, this is the same phenomenon. So it's often referred to as the champagne bottle effect that makes very explosive eruptions. So explosive eruptions mean there's ash in the air, and the ash is traveling, and the ash will then start to fall at some point. And Mount St. Helens was a very useful case study for this. and there was a darkness within about 350 kilometers from the volcano during the day because of all the ash. And the associated ashfall caused large swathes of agricultural land to be inundated. And of course, it has all sorts of other problems. Imagine air filters, drainage systems. All of this is affected by ash. And if you have thick ash on your house, your roof is not usually laid out for this. So let me give you an impression. This is now, and I hope the sound will work, this is now during the La Palma eruption, a little video that we accidentally recorded. It wasn't supposed to be recorded. My PhD student Harry did that. And now you can actually hear how ashfall sounds. So that was a little impression of how it is to be in an ashfall. And here, as I said, we often have a lot of technical problems that result from that: damage to machinery, roof stability, water and drainage pipes, and respiratory problems. People who have issues with breathing, this will of course be particularly bad for them. So here's a few more impressions. Mount St. Helens 1980, and there you see vast amounts of light-colored ash being blown out. And of course, once it rains on top of that, the ash starts to be a slurry, and you get potentially mud flows as well, and this is very unpleasant. So here's a little map, and it shows the speed at which the ash cloud was traveling, and the little boxes in white give you a time. At 9:15 in the morning, it was within about 100 kilometers of Mount St. Helens, and by the evening of that day, about 6:15 in the afternoon, it had traveled for something like 1,000 kilometers. So this is a hazard that will actually affect areas much, much further away than the direct effects that lava flows have on their surrounding. Another very unpleasant phenomenon is pyroclastic flows. These are hot gas and ash-rich clouds that rush down volcanoes. They don't go up into the air, but they travel close to the ground. And on the right-hand side, you see an image from Augustine Volcano in Alaska, where one of those clouds passed through a valley. And the Valley of 10,000 Smokes, you might have heard, was also one of those ash clouds, where there was still hot gases emitted for years after the event. And the first time we really understood this goes back to Pelé, 1902 in Martinique. And there, the city of Saint-Pierre was wiped out in an instant. And only later did we realize that this was these hot ash clouds. And here in 1991 at Pinatubo, we have a similar situation. And these ash clouds, they rush at speeds of 4, 5, potentially 600 kilometers per hour, which means that even your fastest car will not allow you to get away if you're standing in front of it. The car, the blue car there, is my understanding, did not make it. So, as I said, the 1902 disaster in Martinique was very instrumental for us to understand things. And here we see an image of the eruption devastation on the right-hand side in the lower part. On the left, we see the city of Saint-Pierre prior to the eruption. It was a thriving port city, selling a lot of rum and bananas. And after the eruption, not a single house was left standing. And only one person survived. And this was one of those pyroclastic flows rushing through the city at enormous speed and with enormous heat. So here's a few impressions. And we don't have to go into the details, but close to 30,000 people perished in that eruption. Sadly, a lot of people realized the volcano was waking up, but the governor actually decided to not evacuate the city because there was an election coming up, and he wanted to have voters in the city. The election never took place. So, and I'm going to bring you back to Mount St. Helens for a second here. So Mount St. Helens was not only a big ash plume, but it also had a pyroclastic flow, and it actually happened when the volcano collapsed. So here is a little sequence, and you can just about see when the flank of the volcano was sliding down, it started to bring out an ash cloud. So this sequence here is literally just minutes, and there we have a pyroclastic flow coming out from Mount St. Helens as well. So, well, pyroclastic flows are very devastating. The forests around Mount St. Helens were destroyed. There was 2 volcanologists on duty at the time. They were observing the volcano, because observatories means literally you observe, at least in the old days. And these are 2 heroes amongst the volcanology community. This is Harry Truman and David Johnston. And David Johnston, apparently, he had a camera and he was taking photos of the oncoming pyroclastic flow. And just before the pyroclastic flow reached him, he turned around and buried the camera underneath him. And we still have the footage. So amazing scientific achievement, but at a very high price. So this is Mount St. Helens before and after. The stippled line gives you the volcano before the big eruption, and then you can see it afterwards. So you can imagine how much material was removed. And this brings me back to something else, and that is here is a map of Mount St. Helens, and that is indirect effects. We talked about the blast zone from the pyroclastic flow. That's the hatched area. But then in black, we have debris avalanche deposits, and we also have lahar deposits, mud flows. All of these things affect the area in a very, very strong way. So here we have a new dome growing. So Mount St. Helens is not dead. It's not even dormant. There's a new dome pushing up, and this will grow sooner or later to a respectable size and cause another eruption. If you've ever been to Southeast Asia, the country with probably the highest number and most dangerous volcanoes is actually Indonesia. They have 129 active volcanoes, and some of them are very, very dangerous. The image there to the right is from Merapi volcano, and this sits right in the middle of Java Island, and it sits right next to Yogyakarta town, which has about 3.5 million people living in the municipality and the city itself. So here is Merapi volcano in Indonesia. The largest Buddhist temple in the world was actually buried by its eruption in about 1200, and there's a large Hindu temple as well, Prambanan, and this was destroyed several times by large earthquakes that come from the volcano. So this was the Merapi eruption in 2006. There was a pyroclastic flow going through this village, the village of Kali Atem, and as you see, the devastation is just, well, unparalleled. So we have eruptions of this nature as well in the Canary Islands, but luckily, the last of this type is over 100,000 years ago. So in the Canary Islands, we actually have no historical record of large explosive eruptions. The last explosive eruption was in the National Park of Tenerife about 2,000 years ago, but had only a very local effect. And here from Tenerife, from the south of Tenerife, some ash deposits from the older history of the island. And there we can see how thick they are. So Tenerife was very violent in its past, but all the historical eruptions were rather friendly. There's something good about these eruptions, certainly on Tenerife, because the eruptions, of course, they kill all sorts of creatures, including all the animals living there. And because of the eruptions, we got fossils, can you believe it? This is animals that got caught up in the eruption and died. And they're not fossilized in the classic sense, you still find the bones, but there was a giant rat living on the Canaries, and we have skeletons of this animal because of the volcanic eruptions. So, of course, they're devastating for the environment, but for us, for our knowledge, these eruptions often form time capsules, like Pompeii being a time capsule for Roman life, and we wouldn't have that information otherwise. So I'd like to talk a little bit about indirect effects now. Dramatic as eruptions are, often indirect effects are as bad, if not worse, and lahars, volcanic mud flows, they are very, very devastating. Lahar is an Indonesian term because there we often have eruptions, volcanoes, and a lot of water coming together. And there we have rivers of dense mud that travel downhill, and that has the density of concrete, but it's as runny as water, and that makes it very, very dangerous. The prime example that all volcanologists are confronted with is the Armero case. This goes back to the mid-1980s, Nevada del Ruiz in Colombia. It had a small eruption and a mud flow resulted from melting of snow near the crater area on the volcano, and the mud flows were traveling downhill, eventually reaching the city of Armero, killing about 70% of the population there. Some 20,000 people perished within minutes when the mud flow rushed through the city. So here's a few impressions from the mud flows and the devastation it causes. It's a very sad case because the USGS, the US Geological Survey, actually did a contract job for the Colombians, and they had this map that was that is in the top of this diagram, and it shows exactly the hazard areas. It shows the orange for the pyroclastic flows, the red for the lava flows, and in brown the lahar danger zones. And the mayor of Armero had this map, but it was in some drawer in his desk. And when the eruption happened, I think he must have forgotten that it existed. And it led to the catastrophe of Armero. So knowledge is one thing, understanding it is another. If we don't apply it, it's no good. So this is an important lesson. Another disaster, albeit of smaller scale, is the Tangiwai train disaster from 1953. And this is at Ruapeo volcano in New Zealand. Small eruption, again meltwater, it leads to a lahar. Lahar takes out a bridge, a railway bridge, and the Auckland-Wellington express train was just about approaching the bridge at that point. One of the local people realized the problem and gave signals to the train driver. The train driver puts in the emergency brake, but half of the wagons are actually going down into the valley. The other half were actually saved. So, and this is the river. It's not a particularly big river nor a particularly deep valley, but it led to the death of 157 people at the time. So this is the little lake in the top right. This is the crater lake on Ruapeo, and you see the snow there. And of course, an eruption can cause melting of this, and this will travel down within a few hours from the crater area to the lower ground. And if you go to the Ruapeo area, then you'll see deposits like this. So this is a lahar deposit in the geological record. It's not a recent one, it's an older one, but there you see these large blocks that were transported by the mud flow, and you get an idea of the power, of the force behind those mud flows. So we need to be ready for those in volcanically active areas. But the good thing is, all of these disasters, they're mistakes that cause us to learn. So from that point of view, I think we will get better every year a little bit. Another major phenomenon that is rather devastating is tsunami. Tsunami are traditionally thought to be caused by earthquakes, and that's of course true. But volcanoes can also do tsunami. The problem with volcano tsunamis is they tend to be a lot bigger than earthquake tsunami. So tsunami are commonly generated by submarine earthquakes, and they can also come from eruptions of volcanoes. And the term is from Japan, as you probably all know. And why is Japan affected by this? Well, because Japan sits opposite from Hawaii. And actually most of the tsunami that hit Japan are actually from Hawaii. So there's submarine landslides or submarine eruptions, and they cause all sorts of shifting of water masses, and then they travel across the ocean. So this is why Japan is very frequently affected by these. A prime example, again, from all the volcanology textbooks is the 1883 eruption of Krakatau in the Sunda Strait, and there we had a big eruption and a resulting tsunami, and the tsunami was more devastating than the eruption. It wiped out close to 300 coastal villages, killing 36,000 people at the time. Now, this is a hand-drawn sketch, so it's likely a little exaggerated. So the upper one is an image of Krakatau volcano before the big explosion, and then the remnant of it, Rakata Island, is the one below. So a lot of material was blown out, causing a huge tsunami. And there's amazing witness reports about this little ship here, the Beru, a Dutch steamer. And the Beru was actually picked up by the tsunami, and it was actually brought from the Sunda Strait onto shore and was found 1.7 kilometers inland. So you can actually get the idea. Nobody survived there. And there was an expedition a few years ago trying to find the Beru. And they did find it. It was still a rusty old kind of, well, remnant of a ship somewhere in the jungle. And now the coast had shifted. It was actually 2 kilometers inland. And apparently a monkey colony was living in it. But yeah, that must be quite a sight to imagine this ship being taken by a wave all the way kilometers inland. Well, that gives you an idea. However, despite all our knowledge, a new little volcano grew inside the Krakatau caldera. We call it Anak Krakatau, the child of Krakatau. And here in the top right, you see Anak Krakatau. It grew to about 360 meters in height. And many people started to get very worried about it. Western scientists alerted the Indonesian authorities. Unfortunately, not a lot happened. And it collapsed again in 2018, causing another tsunami. This time it killed only about 480 people. But nevertheless, the problem still exists. We are not master of it yet. And this is a big issue. So coming to the Canaries, where we are going, this is the island of Tenerife, and we'll spend 2 days there. And there, let's see, yes, there we have the large caldera, the Las Cañadas caldera, and there Teide volcano sits right in the middle. And this is likely a landslide scar. It actually deposited a lot of material out there in the ocean, and it would have led to a large tsunami as well. Luckily, this was 200,000 years ago, and there's no sign that we will witness something like this in the near future. And we even have some older evidences. There's the beautiful, very scenic and very lush Orotava Valley, which we nowadays believe was also the site of a major landslide, but that one was 530,000 years ago, so that's even further back. So these large landslides on ocean islands, they are real. You might have heard about them. And there was a big fuss about La Palma, also one of the islands we're going, and people believe that there could be a large landslide causing a major tsunami that will travel across the Atlantic and reach the western seaboard, the eastern seaboard of the US. Well, hopefully not, and hopefully certainly not in our lifetime. So this is La Palma. La Palma had a series of eruptions. It's actually the most volcanically active island in the Canaries, and cracks have formed during the 1949 eruption. And let me bring you down here. And it's believed that this part here where the arrow is, this bulky part, that might collapse into the ocean, might fall into the ocean and cause a big splash. But we don't really know how big that splash would actually be, even if it happens. And we have surveillance there right now, and the flank has not moved in tens of years, so it's pretty stable. And this is the predictions. I showed it in my first presentations. This is a numerical model. It's not reality, but the numerical model calculates how long it would take for this wave to go from La Palma all the way to the US. And it's a bit too small, but it says T is 9 hours. So apparently 9 hours after the collapse, there could be a wave reaching the US. So what do we do all about, these hazards? How do we handle this? Well, it's obvious that we have no tool to stop volcanic eruptions. This is impossible. We cannot do this. The government of Hawaii tried to bomb volcanoes in the 1930s. It didn't really work because you can close the conduit, but if there's more magma coming from underneath, it's not very helpful. The suggestion came back during the 2021 eruption on La Palma. The mayor of El Hierro Island, the neighboring island, said, "Why don't you bomb the volcano?" But it's also said that he was not a big fan of La Palma, and so maybe there was a second thought behind this suggestion. In any case, bombing is no good. Other people said we could drill them and let the pressure out, but I don't think you want to drill a volcano that's already under pressure. So I don't think that's a good idea. We have no way of stopping them, so we must realize we must prepare. We must understand the hazards and get out of the way if we can, and this is what we're doing. We're monitoring volcanoes, we are trying to improve our understanding of volcanoes, and we're using increasingly sophisticated technology, and hopefully it will minimize the loss of life and the loss of infrastructure. A few words about this towards the end. It all started here, 1871, that's the Osservatorio Vesuviano, and this is of course in Italy, and back then it was really an observatory in the sense there was somebody sitting there with binoculars watching the volcano, and when something unusual happened, then alert would be given or a note would be made depending on. In the 1930s, the Dutch colonial government in Indonesia had a lot of volcano problems, and they started to build also volcano observatories. And the Japanese, when they conquered the islands, they took over, and they learned a lot about their own volcanoes from the Dutch, actually, in Indonesia. And of course, in the 1920s, the Hawaiian Observatory was opened up, and the French built an observatory also in the 1920s after the disaster at Montagne-Pelée. So this was the heyday of observatories between about 1870 and the 1920s. In those 50 years, a lot of little volcano observatories sprung up. Nowadays, we use a lot of technology, and this is an image from the USGS. So now we use remote sensing. We can use satellites, for example. We can use thermal imaging. We also go on the ground and sample gas. We now have also ways of analyzing gas content from volcanoes remotely, at least qualitatively, and we can see whether there is more sulfur, for example, coming, or whether the volcano heats up. We can also measure seismic activity. If there's magma moving under the volcano, you get a lot of little earthquakes, you get a tremor, and we can, of course, detect that, and then we can make calculations where the magma is and when it arrives. So all of these things together will tell us a volcano is waking up or a volcano is dormant. And these days we can also use multiple overflights by satellites. You take a picture, and in the lower right-hand side we get these fringes of overlay pictures. This shows you about deformation, and it pinpoints the center of a deformation. So here it images an area that's bulging up, likely from magma that's pushing from underneath. So if we have multiple lines of evidence, the seismic shocks, the expansion of an edifice, a volcano edifice, the gas emission changing, the heat flux increasing, then we can be pretty sure something is in the bush, and this allows us to make some sensible statements about how long it might take to a potential eruption. So volcano monitoring therefore looks at various methods, and often it's still ground-based, but increasingly, as I said, it is also remote, and that means you can monitor volcanoes even in the Atacama Desert, and you don't actually have to have personnel there anymore like we had at Mount St. Helens. So I mentioned this is a very important tool these days, and literally all volcanoes in the Western world are looked at with this method these days. This is interferometry. This is an interferogram where we take multiple pictures, as I said, and if there is deformation either up or down, then we can see that, and usually before an eruption the volcano rises, and after an eruption the volcano inflates. Big problem in Iceland right now is that we have an eruption, but the volcano doesn't deflate, which means we will likely have another eruption very soon. So the volcano is not emptying itself sufficiently, and there's likely new magma coming in, so the volcano still swells despite eruptions happening, and that's a very worrying scenario. So here another remote sensing technique, and that is thermal imaging. So whenever there is something anomalous happening in, for example, the crater area, you can see this now with remote sensing methods. So, and then we can also look at ash clouds, and we can monitor ash clouds, and together with the wind we can actually work out to where the ash might travel, and we can warn people downwind and basically say, well, close your windows, get your mask on, and things like that. And here is some survey data from an eruption of the Spur volcano in Alaska, and there is a travel speed here as well, and here the ash cloud was traveling down towards the southern Canada and the northern US, and then it was turning around because of the wind, going up into, well, higher parts of Canada again. These areas are not so densely populated, so it didn't really cause a lot of damage, but here you can actually make some sensible predictions. We talked a little bit about Mount St. Helens, and it was, of course, a classic case for understanding volcanoes better. And there was a second eruption at Mount St. Helens 2 years later. It's entirely unknown to most people, simply because nothing bad happened. It was so well predicted. The US Geological Survey, they really learned their lesson very, very swiftly. And we see here the seismic energy was increasing, the dome expansion was increasing, the tilt of the flanks was increasing, the gas emission, and the USGS colleagues were able to predict the eruption within 2 hours of it happening. So if you have the money, the will, and the manpower, you can predict volcanic eruptions. The only downside is most volcanoes are not in countries that have these components. So, and I'd like to close very briefly here with a short note on the largest eruption we had in the Western Canary Islands in the, well, historical record, and that's the Cumbre Vieja eruption from 2021. There was a whole series of historical eruptions, but this one was really quite spectacular, and unfortunately it happened in an area that was densely populated. It was predicted several weeks before, and people knew it was coming. Scientists knew several years before that magma was moving. Here's an interferogram, we talked about this. So from that, it was possible to even roughly say where the eruption will happen, but evacuations were not practiced. It was a bit tough for people to leave their homes. There was no kind of eruption in the last 50 years or so, so human memory is fickle in those cases. And it led to some complications, but luckily no fatalities during the 2021 eruption. But the damage was enormous, with over €1 billion in damages. But I'll talk a little more about this when we are actually on the island of La Palma. There will be a lecture just on the 2021 eruption. And now I say thank you for your attention, and I'm glad you didn't have that nap that was talked about earlier. So.